Okay, I want you to think of two positive numbers. Actually, they don't even need to be positive. It'll just make it easier for yourself if they're positive integers, where one is bigger than the other. They do have to be different numbers. They can't be the same number. Now, here's an interesting thing, right? If you take the first number and, okay, so here's what you need to do, right? You need to take the second number, multiply that by 2. Take the first number and subtract the first number from this 2 times the second number, right? That's your third number. Okay, that's your third number, okay? Now take your first number and add it to the second number. That's your fourth number, okay? Now you take your second number and square that, and then you multiply 2 times the square. That's your fifth number. Now, if you multiply your third number by your fourth number and add your fifth number, you'll get a number. Now, that sounds, I'm going to call this the sixth number, right? Sounds overly complex, right? Well, here's an easier way to do that. Take your first number and multiply that by your first number minus your second number. That's it. Literally, all that super complex mumbo jumbo equals just your first number times your second number, or first number times your first number minus your second number. Overly complicated. So here's an example, right? So say your first number, say we're just going to say the first number is 25 and the second number is 5 for this example. So in this example, we have, for our first formula, we have 25 minus 2 times 5 times 25 plus 5 plus 5 squared. Well, 15 times 30 plus 50 equals 500. Well, what do you know? 25 times 20 also equals 500. And this becomes apparently visible. This becomes very apparent when you start to look at a table. Like right here, there is a table. Let me sync it, by the way, because I'm also using Excel. So let me sync this real quick. 1, 2, 3. 1, 2, 3. That was a sync. Sync was. I just want to clarify that. Okay, so for here, right here, right? See, this is 225, and this is 224, and this is 221. 210. 208. Now you're starting to notice a pattern here. It's that these numbers are 1 less or 2 less than the one that's 1 to the left and 1 to the right of it. And this, okay, so here, right, this is 196. That's 14 squared, because that's what a squared is. So ignore this, ignore all the rest of this, right? We're just going to focus on 14 squared. Well, you know what, that's a bad example. I'm sorry, ignore that. Let's focus on 15 times 14, because that's a better example. 15 times 14 is 210. Well, as you can see here, this is 16 times 13. The difference between 15 and 14 is 1. So, when you have 16, which is 1, plus 13, which is a difference of 2 from 15, you have 208. If you multiply that by 1 squared, which is 1, times 2, or sorry, if you add that by 1 squared, which is 1, plus 2, you get 210. Now it's interesting, right? Like the difference from the square is represented by the difference that it shows. That was a terrible example. So basically, here's what I'm saying, right? 196 and 195, that's a difference of 1. They are 1 apart. 210, 208, that's a difference of 2. They are 2 apart. 224, 221, that's a difference of 3. They are 3 apart. 238, 234, difference of 4. 252, 247, difference of 5, and so on. And it works for any of these equations. As you can see here, 256, 255, 289, 288. And that's represented here by this equation that I have here. That's not extremely useful. N squared minus 1 equals n plus 1, n minus 1. So that's basically saying here this orange number, 225, is equal to 1 less and 1 above. So basically 1 less than the square and 1 more than the square plus 1, which is true. But I just derived that formula even greater. So here we have x, right here we have x times x plus 1 minus 2. In this case, we're going to have 15 be x, so 15 squared. 15 plus, by the way, that x times x plus 1 minus 2 equals x minus 1 times x plus 2. So in this case right here, we have x times x plus 1. Let's have the x be 15. So 15 times 16 is this green number right here, which is 240, equals minus 2. Subtract this by 2. You see what that would be? That would be 238 if you subtracted 240 by 238. Now, x minus 1 times x plus 2. Well, what do you have? You know, right? 15. 15 minus 1, 14. 15 plus 2, 17. Works for any number. Now, it helps if it's a part of a square, but it doesn't need to be. And all these equations can be derived. Let's take a look at the last one, the last equation I have right here. R times r plus 2 equals r minus 1 times r plus 3 plus 3. So let's have r, in this case, be this 255 right here. So in this case, r is 15. It's 15 times 15 plus 2, which is 17. So 15 times 17, 255. Well, r minus 1, 15 minus 1, 14. R plus 3, 18. Plus 3, if you take this yellow number and add 3 to it, then we could get 255. Now, obviously, you might be noticing, hey, we're starting to get repetitive numbers here. Well, that's because you can all derive all of this from this equation, and it's a simple equation. Now, that doesn't necessarily mean that it's the correct equation, but it's an equation that works. Is it useful? Probably not. There's also this equation right here that I want to take a look at. H times h plus t equals h minus 1 times h plus t plus 1 minus t plus 1. So in the example I have here, 14 times 14 plus 3 equals 14 minus 1 times 14 plus 3 plus 1 minus 3 plus 1. Is that correct? Minus 3 plus 1 minus 4. I think I messed this one up. I think this one should be plus. All right, I made that plus. Okay, cool. So now you can start to see where some of these equations are starting to take more interesting shapes, as I would like to say. You can mess around with this formula. I got these specific equations in here. By the way, you can double check. I did the math, but I can have here, as you can see here, I typed it into the calculator, 15 times 30 plus 2 times 25, which is where I got that from here, right? That equals 500. And this one as well equals 25 times 20, 500. You know, you can do your own logic check. I did my own logic check. I just kind of messed it up. See, for the equation, okay, so in the equation, I did plus 4, so I just messed it up when I wrote it down. Because in the equation, I did it correctly. I was like, okay, cool. That's pretty much it, really. Although I do want to show you this real quick. This isn't extremely useful unless if you're converting time to minutes and seconds, okay? So if you're converting time, so for minutes you have, this is how you do it. You do equals truncate, and then whatever your series is for your y-axis divided by 60. For the seconds, because that's simple, that's what it is. You divide it by 60, that's the amount of minutes, not including the seconds. So this is where the seconds gets complicated. You have to take the full seconds minus the truncated version of the full seconds divided by 60, and then multiply that by 60. So basically, you're just taking, like, for example, if you had 6.66 as your answer, you're subtracting the 6, and then you're multiplying the 0.66 times 60, and that would be what your value of seconds would be. As you can see here, it fully worked for these equations, which, oh, that's the wrong one. That's why I was like, well, that's not correct. So as you can see here, y26 does it correctly. Anyways, ignore that. And then for full seconds, it's really easy actually. For full seconds, you just multiply the full seconds by you multiply the minutes by 60 and then add the seconds. It's really easy actually. So say you have exactly 8 minutes. Well, guess what? You have 480 seconds. You just add 8 times 60 and then add the 0 seconds, which is 0. So it's just 8 times 60, which is 480. Makes sense. Hope you guys enjoyed that. It was kind of complicated, but it just made you think a little bit, or it didn't. By the way, the equals if symbols just doesn't work sometimes. It's kind of annoying. This is apparently like how one of the ways that you can get it to be odd, this ridiculously complex equation. I'm going to very briefly go over this. So basically, here's what I think of when I say even, right? When I say even, that means that when I divide it by 2, it equals, so when I divide it by 2, it equals 0.5. Is that correct? So I'm trying to look at this equation and find out what exactly my logic was here when I did this. So M24, now logically, let me try to think about this logically for a second here. So say, for example, we have 3 as our number, which happens to be one of the numbers that we have here. So 3 over 2 is 1.5. 1.5 truncated is 0.5. That makes sense, because truncated means that okay, that makes sense, because basically you're taking the 1 minus the 1.5, or the 1.5 minus the 1. Okay, cool. So let's just do an example real quick. So we have 3 over 2. So we have equals 3 over 2. 1.5, right? Now, say we wanted to subtract that by equals this minus the truncated version of this to 0 decimal places. 0.5. You know why? Because it's the truncated version of 1.5 minus 1, because the truncated version is 1. The truncated version of 1.5 is 1. You get rid of the decimals, it's 1. So basically, if the distance between the actual equation and the truncated version is 0.5, then it's exactly odd. If it's not, then it could be even. If it's not even or odd, then it's a decimal, I believe. That makes sense, right? Yes, it does, because the truncated version of, for example, 4 over 2. So let's do another example for even. So equals 4 over 2. 2. Okay, cool. So equals, so let's do equals that 2 minus the truncated version of this to 0 decimal places. It's 0. Gotcha. So that's basically the very difficult way of how to format. Like I said, it says complex. There is an even function. You can literally type in even, and it'll tell you if the function is even or not. But that's the very complex complex way on how to show this. This took 15 minutes to record. Boy. Anyways, hope you enjoy that, I guess. Boy.